All right, today we are taking on a massive, honestly, mind-bending paradigm shift. We're decoding some pretty dense quantum theory to explore the extended superposition principle and this absolutely incredible concept of cosmic self-configuration. If standard physics has ever felt a little incomplete or unsatisfying to you, well, you are exactly in the right place.
Okay, let's dive right into our roadmap for this explainer. We'll start with the superposition problem and the flaw of randomness. Then we'll unpack something called the trap of Markovianism. After that, we'll reveal the extended superposition principle, and finally, see how it all points to a self-configuring cosmos.
Now, before we get too deep into the mathematical weeds, we have to start with the ultimate quantum mystery. What actually collapses the wave function? When a particle is just hovering in this state of probability between different possibilities, where does the universe find that extra tie-breaking measure of determinacy to actually choose the particle's next state? Keep this question right at the front of your mind, because it's the engine driving our entire explainer today.
So let's get into section 1, the superposition problem.
To really understand this problem, we need to look at what physicists call mixed states. Basically, quantum mechanics allows the possible states of a system to overlap. This creates a mixed state where parameters can hold a bunch of different values all at once. But here's the catch. Standard quantum mechanics actually lacks a cogent model for interpreting these. Just looking at them as waves doesn't really explain what's truly going on beneath the surface. And that brings us to a fatal flaw. We can call it the uncertainty principle gap. Standard uncertainty dictates that the last states of interacting particles simply do not hold enough information to fully determine their next states. The info just isn't there in the preceding moment to give us a complete deterministic picture of what happens next. It's basically a massive missing link in the chain of causality.
Which brings us right back to our fundamental mystery, right? If the previous state doesn't hold enough information to dictate the next state, well, how are their next states actually determined? How does the universe bridge that gap and decide what happens next?
That takes us to section 2, the flaw of randomness.
Now, some people argue that particles just randomly choose their next state to close that gap. But let's be honest, randomness is an incredibly insufficient answer. It basically amounts to pure acausality, or what physicists like to call informational incompressibility. Think of it like a giant causal blind spot. Relying on the magic of randomness isn't just a lazy workaround, it's actually unscientific because it completely ignores the need for higher orders of causation.
Moving on to section 3, the trap of Markovianism. This hidden trap is rooted in something called physical Markovianism. It's a core assumption baked right into standard quantum mechanics. It assumes that mixed states only exist between perfectly adjacent events. And by doing this, physicists are ignoring non-random relationships that stretch across time. It completely blinds us to wider, deeper connections.
Let's actually visualize this constraint. In the standard Markovian view, you have a past event where a state is determined. Then, you look at an adjacent event, right next to it in time, where a mixed state is observed. Finally, the next adjacent event occurs and the wave function collapses. Physical Markovianism forces us to only look at these events in strict isolation, one immediately after the other, literally like a ticking clock. It strictly forbids us from looking at broader cross-temporal connections.
So why do conservative interpretations of quantum mechanics fall into this trap? Well, one big reason is space-time geometry itself. In standard physics, space-time geometry appears to confine objects to one-dimensional world lines. Because of this geometry, their state transition events are separated by intervening segments of space and time. Conservative physicists use these geometric intervals to prevent events from globally mixing. It's like they want to keep everything safely isolated on its own little one-dimensional track.
But here's where things get wild. Section 4, Extended Superposition Principle.
Enter conspansive duality. This is where the theory gets truly fascinating. Conspansive duality actually removes those strict geometric restrictions. Instead of isolating events on one-dimensional tracks, it places state transition events in direct descriptive contact with each other. This dynamic overrides those rigid boundaries, rendering the separative intervals completely powerless. It's a real game changer.
And this brilliantly illustrates the difference. Standard superposition is rigidly confined to adjacent state transitions, locked onto those isolated 1D world lines. But the extended superposition principle, it shatters those boundaries.
It puts temporally remote events in contact, enabling coherent, cross-temporal feedback across the entire universe. So you're probably wondering, what is actually pulling these cross-temporal strings? The answer is telons. You can kind of think of telons as higher-order attractors, these underlying relationships that pull objects and events toward a specific purpose or design. According to the text, these telons actively guide both cosmic and biological evolution. So it isn't blind randomness at all. It's a profound connectivity acting as a universal guide. Which brings us to our grand finale, Section 5, a self-configuring cosmos.
Let's see how this builds into an entirely new paradigm. Step 1. Extended superposition breaks the chains of Markovianism, opening the door to higher-order relationships. Step 2. We recognize that events are distributed seamlessly across time. And Step 3. The ultimate conclusion. The cosmos doesn't operate on absurd randomness. By embracing these non-adjacent connections, we actively open the door to meaning and design.
Just look at the poetic beauty of this quote directly from the source material. Extending the superposition concept, quote, makes cosmogony a distributed, coherent, ongoing event rather than a spent and discarded moment from the ancient history of the cosmos, unquote. I mean, think about how profound that is. Creation isn't just a big bang that happened billions of years ago and then just ended. The creation of the universe, cosmogony, is happening right now, continuously, everywhere. And here is exactly where you come in. Because this logical, cross-temporal relationship is true, it totally justifies the observer's role. An observer in the present, meaning you, looking up at the night sky through a telescope, can perceptually collapse the wave functions of ancient photon emission events. By observing the universe right now, you are actively participating in the ongoing creation of the cosmos, reaching back across time to finalize an event that started literally billions of years ago. So we leave you with this spectacular thought. If standard randomness is an illusion and extended superposition connects our current observations to the distant past, how is your observation right now shaping the ancient history of the cosmos? Thank you so much for joining us for this explainer. Keep observing, keep questioning, and we'll see you next time.